hour. Okay, so we're deriving our centripetal acceleration. Please try to draw it yourself. The better you can do, the better you can draw, the better it works. So we're going to draw a circle, has radius r. I'm going to try to envision there the x-axis a little bit. Okay, but it's better to use the radial axis. Like radially inward is positive, radially outward is negative. Okay, because we have an object of mass m. We're going to start it. For somewhat helpful reasons, we're going to start it on the x-axis, and our velocity, we're going to call that v1. There's our starting velocity. The velocity, if you're going to move along a circle, then your velocity has to be perpendicular to the circle. You move along the track, perpendicular to the radius of the circle, excuse me. You move along the track around. You don't move farther in or farther out, okay? It's a circle. It has a constant radius. Okay, that's the, the definition of a circle, in fact. Okay, at some later time, my mass has moved over. Whoop, whoa. So I made that mistake again. Draw the mass at a different position later, and draw its new, okay, it's the same radius, but it's at a different angle. We're actually going to name that angle theta to use later in the problem. And then try and draw your speed perpendicular to that. There's velocity 2 at some later time. Okay, that's pretty good. I maybe should have left myself, no, it'll work. It'll work. Okay, and those are supposed to be perpendicular. Yeah. Okay. It'll be okay. All right. So we are solving for the physics acceleration. And actually, that would be the magnitude of the acceleration. Okay, we won't worry about magnitude so much. But to get acceleration, I seriously just want the change in velocity over the change in time. Okay, and it's velocity that I'm really concerned with. Okay, because to get delta v, a vector, I can always evaluate its magnitude at the end. I have to take v2 minus v1, right? Oh, and now that's the most important part, because remember, we have constant speed. So the magnitude of v2 equals the magnitude of v1. So if we didn't change direction, that difference there should be 0. That's what it means to go in a circle at constant speed. Okay, we'll take our special case at first. Does anyone in the room remember how to add and subtract vectors? It's been a while. If I was going to add v1 plus v2, what would I have to do? Sure. Okay. That is the breakdown. Algebraically, I could break them into x and y components. Ooh, look, v1 would have only y. And add them together and get a sum. Okay, what if I'm going to do this geometrically? Okay, that amounts to, if I was going to add v1 plus v2, I would take my v2 vector and place it on top of the v1, like nose to tail, and then draw the diagonal. That would be the result. So if I want to take v2 minus v1, to get the difference, I actually have to, there's my smaller, I have to make up a new vector and call it minus v1. Okay, and that's why I drew this guy with some space. Here's minus v1. It's v1, but it points exactly the opposite direction. And I'm going to copy that vector over here. Here's minus v1. They should be the same length. v1 goes straight down, minus v1. Okay. And then, from where the mass is now, there's v2 minus v1. This guy is delta v. That's my difference from the start of both to the end. Oh, look. I mean, it kind of looks, I got a lot more proof to go, but it kind of looks like it points, like if I was swinging along this path, it kind of looks like it points back toward the center. Not exactly. It's kind of a problem, but close. I could be on the right path. Okay. So, I've got to copy this triangle where it's V2 and V1 and delta V. Okay. And let's see. Oh, keep in mind how these are right angles everywhere. This is a right angle between the radius and the velocity, and so is this. I deliberately didn't swing all the way to 90 degrees away. In fact, actually, the closer together V1 and V2 are, the better. Okay. Whoop. Does anybody still need to write or draw? Okay. A few. So I moved along the circle. My velocity changed from V1 to V2. They have the same magnitude, sure. I'm going to recopy that triangle where I drew my vectors because we need to inspect it really carefully. What we're looking for is where is this angle theta? Because I'm actually interested in like the instantaneous acceleration. Okay, what is really the acceleration of m at point 1 at this first... Whoops, oh, I'm going to scroll the screen. Where it is with V1, what's the acceleration there? Is it straight toward the middle? Because it doesn't look like it's straight towards the middle. I mean, it's close. It's not way off. Okay. I'm going to have to zoom in, scroll up. Okay, and we got a bunch more room. Okay. Well, we've got to look really carefully at this triangle. If I make this triangle, it's an isosceles triangle. Do you see that? Because the length of each vector, so here's V2, vector, and its magnitude is just V. Straight down in my original graph, oh look, there's V1, and its magnitude is V. So I just copied it over. One of these angles, so if those are equal sides, these angles at the bottom have to be the same. And here's my delta V vector that I'm kind of solving for. Does one of those angles have to be theta? I think it does. Okay, look, so theta is the angle between these two radii here, to point 1 and point 2. We can call this is point 1, and this is point 2. The velocities are both perpendicular to those same radii. So like basically these radius lines cross at angle theta. And then those two velocity lines are perpendicular. Don't they also have to cross at angle theta? Uh-oh. Yeah, they do. If I have two angles, if I have two lines that cross at this angle, and then I draw two more lines that are perpendicular to those lines, my perpendiculars also have to cross at the same angle at some point. You can do the geometry construction if you want. I don't think I have room. That top one is theta. Okay? I'm really sure. If you brought rulers and protractors, compasses, I used to teach geometry myself. When I was in school, we got out the compasses and scratched out the little circles and did all the little tricks. I thought it was awesome. Everyone else hated it. So then when I became a geometry teacher, I don't make people do the compasses and protractors unless they really want, like maybe a bonus project or something. Because, I don't know. If it's so frustrating, because you're making lots of little mistakes, then I bet it's not enlightening. But I really like to draw and build it myself. So if you're curious how I'm doing this, try the geometry yourself. It's awesome. Okay, here's where we get mathematical. Okay, so far we just drew triangles. We did some similar stuff. You did geometry. We want the instantaneous acceleration. We're targeting a specific instance. So delta t and actually theta will be very small. They don't have to be 0. They can't be 0. But we could make theta like 0.001 radians. And we could make time like zero point 0, whatever it needs to be. Okay, very, very small seconds. And actually, you watch the computer graph in those ball toss graphs. The ball toss graph was only like 0.05 seconds between data points, and it looks like a smooth line. And for your brain and your eyes, you can't track times that fast. Nobody can. Okay, not that fast. Okay, well, so here's my trick. If theta is very, very small, this angle gets very, very close to 0, what do these angles in the corners almost turn out to be? 45 each? If I have this one as almost 0, the other two corners of the triangle, it's hard to believe. Yeah. What? Let's not mess with our brains too much. Let's make one of them 90. But we gotta know that actually, so they're at like 89.99999. Okay, they're close enough to 90. These guys turn into 90-degree angles. So actually, this is the physics that I want. The magnitude of my delta V is going to equal just V, because I could use either side now. That's an isosceles triangle. It has the same two angles, has the same two sides. The magnitude is going to be V sine theta, because this delta V is the opposite side from my little theta angle. And theta is super, super small. Have you ever done the very small angle approximation? If theta is very, very small, and in radians, then you can just write V theta. And you can actually try this in your calculator. Put it in radians, take the sine of very, very small angles, and they're basically less than a tenth, and they're basically the same. The sine is the same as the radians. Okay? Because, oh no, I gotta pause the video and do part 2. Okay. We'll examine arcs and radians in a bit. Okay, but we've got our delta V. It's just V times theta.